The word computer in the B-29's world did not mean glowing tubes and typed commands. It meant a set of small, stubborn machines that could do math without words. They lived behind panels and in sighting heads, built from brass cams, steel gears, spinning gyros, and little electric motors that turned numbers into motion. When crews spoke about the bomber's computer, they meant the combined brain made by three linked parts: a precision bomb sight that could solve a moving geometry problem, an autopilot that could hold the aircraft perfectly steady, and a fire control system that let remote turrets lead a fast enemy and put bullets in the air where a fighter would be, not where it was a heartbeat ago. None of these boxes thought in the way we imagine thinking today. They balanced forces and angles. They used spinning wheels to sense pitch and yaw. They took in airspeed, altitude, wind, and drift as physical inputs, and they produced outputs as electrical signals, moving veins, and steady hands on control surfaces. They were practical mathematics with teeth and bearings. Start at the nose, where the bombardier sat in a glass blister with the bomb sight in front of his chest. Inside that compact head were gyroscopes that wanted to stay upright, like tops that refused to tip. There were tiny discs and drums shaped to encode equations. When the bombardier set in his altitude, true airspeed, and estimated wind, the sight did not store the values so much as reshape itself, aligning small cams so that when the aircraft moved, the sight's internal parts moved in a way that matched the math. It was a physical formula you could touch, but the sight did more than compute a time and a point to let go of the bombs. It could also tell the airplane how to fly the last, sensitive part of the run. That is where the autopilot joined the act. The two were wired together so that, with a switch, the brain in the bomb sight sent tiny orders to the airplane's control system. Those orders were not words. They were small electrical signals that told servo units to nudge the ailerons and elevators by exact amounts. In effect, the bombardier's calculation reached out and steadied the wings, holding the aircraft on a track that matched the moving solution. Behind the nose, down a long pressurized tube, sat another part of this quiet brain: the central fire, control equipment that guided the B-29's remote turrets. There, too, were gyros to keep the sights level, small motors to move guns with smoothness, and differential gears that added and subtracted angles. A gunner did not yank a trigger on a heavy, swaying barrel. He sat at a sighting station, put the attacking fighter in the crosshairs, and the computer in his station worked out how far ahead the guns should point, because bullets need time to travel, and an enemy does not sit still. That calculation seems simple when said fast. It is not simple when a fighter is crossing above or below, climbing or turning, and the bomber itself is pitching in thin air. The B-29's fire control machine solved this with a mix of electrical signals, rate sensors, and geometry hardwired into the metal shapes of gears. Again, there were no lines of code. There were shafts and follow-up mechanisms that kept asking, "Are we on the right angle yet?" and drove the guns to stay there. What tied all this together was discipline about inputs. A computer is only as good as what you tell it. The crew learned to feed the sight with honest numbers. They took drift readings. They checked pressure altitude. They used true, not guessed, airspeed. The bomb sight then handled the part humans struggled with at 20,000 feet. It held the arithmetic together for the seconds that mattered. Those seconds were when attention is hardest to keep. Eyes water in the cold. The ship may shudder in a gust. A pilot's hands, no matter how skilled, have rhythm and tremor. The linked bomb sight and autopilot had none. It just held. And because it held, the geometry it had set up in its brass and steel stayed valid until the last piece clicked into place and the bombs stepped off the racks. If you pulled a B-29 from the sky and laid its brains on a bench, each small unit would make sense by itself. A gyro wants to stay level. A cam turns rotation into a curve. But the real trick was not the parts. The trick was how the parts were arranged in a conversation. The bomb sight did not merely show a solution. It reached forward and shaped the airplane's path. The autopilot did not simply hold a heading. It listened for tiny corrections based on wind and drift, and it made those corrections without tiring or second-guessing. The turret system did not wait for a human to judge a lead by feel. It took the observed rate and translated it into gun motion, so that human eyes could focus on tracking with calm hands, while the machine did the tiring math. That is why crew members called the combined effect a computer. It felt like one thing, though it was many. Precision came from the fit between these units and the crew's habits. Before a mission, men in coveralls with toolkits zeroed the sights, spun the gyros up, checked for play in the linkages, and matched the autopilot to the aircraft so that there was no slack between an electrical nudge and a movement of the elevator. In the air, the navigator and bombardier took time to measure drift rather than guess it, because the sight would reward honest inputs with a correct solution. In the gunners' stations, crews trained to keep the target centered in a stabilized sight, trusting that the computer would move the barrels to the true aiming point even when the fighter's path curved. None of this looked like what we call computing now. All of it behaved like computing then. It turned messy, changing air into steady answers. When Japanese engineers later examined captured equipment, they could measure the diameter of a gear or the voltage of a servo. They could draw the shape of a cam. But the hardest part to draw was the living fit between all the boxes when the airplane, the air, and the humans were working as one. The B-29's computer was not magic. It was honest engineering, assembled into a system that made math live. That is the plain truth at the core of the story. And it is why, once you see the pieces together, the word computer feels exactly right for a set of spinning gyros and humming servos built to keep faith with a line of numbers in the sky. By the time the B-29 reached full stride, the war in the Pacific had grown into a problem of distance, weather, and will. Targets lay across long stretches of ocean, beyond island chains that acted like stepping stones but not like shelter. The bomber had to take off heavy with fuel, climb into thin air to stretch its range and safety, and fight the wind that could be wicked over Japan in winter. A high river in the sky, strong enough to push a bomb pattern sideways and make a perfect release miss by streets. Crews could not rely on bravado to beat the jet stream. They needed a calm way to fly a straight final run while drift tried to slide them off the line, and they needed to drop at the 1 second when the moving geometry agreed that the bombs, the wind, and the target would all meet. A single hard-won run could carry the work of hundreds of men who had packed those bombs, loaded fuel, and kept the engines honest. Precision was not a nice extra. It was respect for the cost in hours and lives. High altitude brought its own tricks. The air is thin, so every nudge on the controls can overdo it. A pilot hand-flying a steady line for minutes in light chop tends to soar at the controls, even when trained not to. That little hunt left and right is the enemy of accuracy. The B-29's linked bombsight and autopilot took that hunt away. The sight said in its quiet, mechanical way, "Hold this exact line," and the autopilot did, turning little electrical orders into smooth deflections that did not overshoot. The effect seems small if you picture a line on a map. Inside the airplane, it was the difference between a human body wrestling with drift and a machine that does not get tired. The crew could pour their attention into getting the inputs right: true wind, true speed, true altitude, because they did not need to micromanage the last half mile of flight. That freed attention is part of what precision really is in war. Not just better numbers, but better attention for the things only people can do. Weather was more than a line in a briefing. Over Japan, cloud decks could hang thick and stubborn. In some periods, radar sets were coupled into the bombing system to give eyes when the glass nose saw only white. Even then, the habit of precision mattered. If you train to tell your machine the truth and you trust it to hold the line, the move to radar-assisted drops still rests on the same discipline. Steady flight, clean inputs, and releases that happen because a solved geometry problem reaches zero error, not because someone's gut says now. Precision is a culture as much as a device. By late 1944 and into 1945, that culture had to be strong enough to keep its shape across hundreds of aircraft, new crews, maintenance shifts at night, and all the human mismatch that a huge air campaign creates. Against that effort, stood defenders with speed and claws. Fighters that slashed in from angles at the moment when a bomber wanted to be steady could spoil everything. The B-29's remote turrets and their own analog brains mattered here. If gunners could keep their sights level and their target tracked, the computers would swing the guns with the right lead, cutting down on the guess and prey that wastes ammunition and nerves. A defended bomber can afford to fly a straighter line for longer because it is not counting on wild maneuvers to shake a pursuer. Every second of steadiness is a gift to the bomb sight and a punishment to the fighter pilot who expected a weaving target. Again, precision came from the system, not from a single heroic act. The bomber's brain and the gunner's brain supported each other so that the whole ship could behave like a calm instrument rather than a frightened animal. There was also the matter of logistics and time. Islands in the Marianas were busy engines of supply. Fuel arrived by the ton. Bombs and spare parts came across oceans. Ground crews worked in heat and rain and dust to swap engines, set clearances, and true up sights. An accurate airplane pays back that work by making each mission count. Fewer runs for the same effect saves engines and airframes, and it saves men who might otherwise fly one mission too many. The math here is simple, in the large, and complex in the small. In the large, a formation that can keep its bombing error tight will need fewer total sorties to achieve the same damage. In the small, a ship that can hold its line and release on a clean solution reduces the odd chance of a stray stick running across a neighborhood that was not the target. Precision is humane, as well as effective. It confines violence to a chosen point and time, rather than spraying it around the map. On the other side of the lines, engineers who took apart captured parts were not blind to what this meant. If the bombsight and autopilot could make a complicated run feel simple, then crews could repeat the same performance day after day. Repeatable accuracy is the scary phrase. It means your enemy has turned skill into procedure and procedure into output. It means the factory that builds the bombsight has the tolerances, the test rigs, and the trained hands to produce hundreds and still have each one behave like its brother. It means the school that teaches new bombardiers has a method that produces the same calm steps under stress. It means maintenance crews know what right feels like when a gyro spins or a servo hums. That network of factories, schools, checklists, and habits is what precision rests on. By 1944-45, that network was large, and the B-29 was designed to take full advantage of it. In the air war, there is always debate about doctrine, altitude, and the best way to reach an end. Those debates matter, and they shifted with season and threat. Yet inside every approach was the same small truth. If you can hold a steady path in the last minute and let a solved equation control the release, your chances of hitting what you aim at go up. The B-29's computer made that last minute less fragile. It turned a human's task into a partnership with a machine that does not blink in cold wind. That is why it mattered so much. In those years when distance and weather and defense all did their best to make a straight line into a crooked one, the bomber's quiet brain did not win a war by itself. It did something humbler and just as powerful. It made discipline pay off. Every time the nose came onto the run and the sky began to shake. The B-29's brain was not a single box but a set of linked devices, each with a clear job, and each designed to behave the same way in every airplane. Up front, the bombsight was a stabilized calculator the size of a small stool. It accepted altitude, true airspeed, and wind as settings, then used spinning gyros and shaped cams to keep its view steady and its math alive even when the aircraft bobbed. It spoke to the autopilot through wires that carried small electrical corrections. Those corrections were not dramatic. They were gentle, continuous nudges that held wings and nose to a path the bombardier wanted. So the final approach did not depend on a pilot's perfect hands in thin air. Under and behind the crew, in a pressurized tunnel, sat the fire control equipment for the remote turrets. That gear took the target's movement seen through a stabilized sight and turned it into lead angles for the guns, moving the barrels smoothly so a gunner could track with confidence. Together, These units made a flying weapon that solved problems in real time, not on a chalkboard before takeoff. Each device had a rhythm. The bomb site's rhythm was set during the bomb run. Measure drift, confirm speed, lock the site to the world, coupled to the autopilot, and let the machine hold the line while the bombardier watched the picture. The autopilot's rhythm was set before flight by mechanics who matched its servo response to the airplane's feel, and in flight by switches that chose whether the bomb site's whispers would guide the ship. The turret computer's rhythm came alive when a fighter appeared, because its internal comparators kept asking if the site's crosshairs and the gun's bore were aligned at the correct future point, and if not, drove the motors until they were. None of this was guesswork. Each rhythm was taught in schools and reinforced by checklists that told crews what to do and in what order. If you wanted to carry a pocket summary into a briefing tent, it would read like this in simple speech. The bomb sight is a small machine that stays level, receives the numbers for height, speed, and wind, and then behaves like a person holding a perfect ruler across moving ground. The autopilot is a steady hand that never tires and can follow the bomb site's tiny orders for the last half mile. The turret system is a set of level eyes and fast arms that offsets the guns to where a fighter is going, not where it is now. The value of these parts is not only that they are clever, but that they repeat their cleverness the same way in every airplane when maintained and used as trained. That last clause matters more than it first appears. A single brilliant device is a curiosity. A simple device that works the same after a sandstorm, a hard landing, or a long mission is a partner. The B-29's computers were built to be partners. Dates and places help fix the picture. The bomber entered combat with the intention to exploit high altitude and long range. As the campaign unfolded, the system adapted, adding radar-assisted aiming when clouds demanded it, and proving that the bomb site autopilot bond was not a fragile trick, but a habit worth keeping whenever visibility returned. The turret system matured alongside the crews, who learned to trust the smooth motion even when adrenaline wanted a jerkier hand. Reliability improved with experience, and with the work of mechanics who learned which connectors needed extra care and which gyros did not like rough handling. None of these facts are glamorous. All of them speak to the word computer as it was lived in the airplane, a promise that if you set it up right and flew it right, the math would be there when you needed it. Think about this fast facts parcel as a handful of anchors for all the detail that follows. The B-29's brain was analog, not digital, which means it used smooth physical motion to represent numbers. It was stabilized, which means it refused to be fooled by moment-to-moment bumps. It was coupled, which means it did not merely advise but could act on the airplane when told to do so. And it was teachable, which means crews could learn a method that produced the same result across months and missions. If you carry only those points forward, you will read the rest of the story with the right lens, because you will be watching for the places where smooth motion, steadiness, coupling, and method turn a hard problem into a repeatable act. One more plain truth belongs in a summary meant to be remembered. The system was forgiving to those who respected it, and merciless to those who lied to it. If you guessed your wind, the site would make a neat solution for a wrong number and deliver a neat miss. If you let the airplane wander in the last minute, the coupling could not save you from yourself. Precision was never free. It was the price paid by honest inputs and steady flying, returned as a tight group on the ground where the target stood. That exchange, repeated over and over, is what made the machine seem uncanny to those who handled a single captured part on a bench and wondered how it could have done so much in the air. The answer was never really inside one box. It was in how the boxes held hands. To understand how the bomb site solved its problem, picture a slow, careful dance between the sky and a small set of spinning tops. The tops are the gyros in the site, whirring at high speed so that they want to keep their axis fixed in space. When the airplane pitches or rolls, these gyros feel the change and push against it, moving the site's internal gimbals to keep the view level. Level is not a luxury, it is the beginning of truth. If the horizon slides and tilts under your reticle, your angles lie to you. The site's first gift is to fight that lie and present a calm, stable world to look at, no matter how the air nudges the ship. With the view steady, the bombardier dials in altitude and true airspeed. These settings do not go into memory chips. They turn little shaped pieces of metal cams and levers so that the internal paths the sight will use now match the mathematics for that height and speed. Think of it as laying down a groove for the problem's solution to run in. Wind is the wild card, so the crew measures it, often by taking drift readings on track lines or by using a drift meter to see how the ground slides under them. The bombardier then trims out the drift by adjusting the sight until the ground seems to flow straight back under the pipper during a test run. When that flow looks true, the sight's internal math now includes the sideways push of the air. At this point, the machine knows, in its physical way, how long a bomb will fall from this height at this speed, and how far it will slide sideways in the wind. The remaining work is to bring the airplane to the exact path where dropping at the calculated instant will put bomb and target together. This is where coupling the sight to the autopilot turns theory into steady wings. The autopilot itself is a set of sensors and servos that take a desired attitude and heading and hold them with tiny control inputs, far smaller and more frequent than a human would make. When coupled, the bomb sight whispers corrections. A hair left, a touch down, a breath of right rudder. These are not big moves. They are continuous, almost invisible nudges that cancel the subtle drift and hunt of hand flying. The bombardier watches the target's image in the sight. As the geometry collapses toward the release point, his job is not to wrestle the airplane but to keep his inputs honest and his eye calm. The sight, with its gyros, holds the picture level. The autopilot holds the path. The machine's integrators, which are just a grand name for the parts that turn steady rates into distances and angles, keep accumulating the truth about motion until the answer hits zero now, and the mechanism trips the release. Inside the sight are follow-up systems that act like polite arguments. A little motor moves a part to a commanded position, while another sensor asks, "Are we there yet?" If the answer is no, the motor keeps working. If yes, it stops. This constant, gentle disagreement is how the machine avoids overshoot and settles precisely on the right value. The same principle lives in the turret computers, where the sight sees the enemy's rate across the field of view, and the computer translates that rate into an offset for the guns. There, too, the follow-up mechanism keeps asking until the barrels point at the predicted spot where the fighter will be when the bullets arrive. The beauty of this method is that it does not tire and it does not get excited. It just keeps asking the same question and moving until the answer is true. Calibration makes this world work. On the ground, armourers and instrument men check that a known input, say a test voltage, or a set angle produces the right deflection in a gauge or the right motion in a servo. They shim a gyro if it precesses too much. They replace brushes in a motor before it fails. They tighten a connector that has developed play. In the airplane, the crew confirms that the sight's level agrees with the physical spirit level, that the autopilot holds a chosen heading without slow wandering, and that the coupling engages without a lurch. This is fussy work, and it must be fussy. A small slack in a linkage or a slow drift in a gyro will grow into a large miss because the problem the sight solves is sensitive in the last seconds. The analog brain does not forgive slop. It rewards care with calm behavior. When the run begins in earnest, every part of the system takes its place. The pilot brings the ship to the initial point and hands the final to the bombardier. The navigator confirms winds. The bombardier couples the sight and watches the pipper settle into its patient crawl toward the aim point, while the autopilot irons out the last wiggles in the path. He does not jab at the controls. He feeds the machine the truth. The seconds stretch, because they always do, until the quiet click of the release cuts across the sound of 4 big engines and the bombs step away. In that instant, the analog brain has done exactly what it was built to do. It has taken a shapeless world of moving air and moving ground and turned it into a solved, repeatable act. There is a reason people who handled this gear later spoke about it with a kind of surprised respect. Nothing about it is mystical. A teenager with a good sense of touch could feel the smoothness of a well-tuned servo. A mechanic with a file could true a cam. A bombardier with patience could measure drift. Yet when these ordinary acts are linked in the right order, the effect seems greater than the pieces. That is what a computer is at heart. A careful arrangement of simple truths that together produce something steady in a restless world. The B-29's analog brain was not there to impress. It was there to keep its promises in wind and cold and fear. And it did. Again and again, because people made it honest, and it paid them back in precision. Long before a gunner saw a fighter as a black cross angling in from the sun, the airplane had already begun to solve for where the bullets needed to be. The solution did not live in a single turret, nor in any one man's grip. It lived in a quiet conversation between stabilized sights, rate sensors, amplifiers, and servo-driven mounts, all of it supervised by a central fire control scheme that treated the B-29's guns as a coordinated instrument rather than a handful of isolated weapons. What looked like a swivel of metal and a glass eyepiece was actually the front end of an analog calculation, and that calculation started the moment a gunner laid a reticle over an attacker and held it there with steady hands. The sights were the first miracle, though they did not feel like miracles to the men who trained with them for hours until the motion became habit. A sight that stays level in turbulence is not just a comfort, it is the condition for truth. Inside each sighting head, gyros spun themselves stubborn, making the picture hold steady while the bomber rose and fell, rolled and yawed. With a level picture, the rate of the target's movement across the glass had meaning, because it was no longer smeared by the bomber's own small gyrations. That measured rate was the seed from which the rest of the geometry grew. The computer took that rate, combined it with the known muzzle velocity, the target's relative aspect, and the movements of the bomber itself, and produced a lead and offset into the future. You could watch a fighter cross left to right and feel the turret, under your fingertips, follow, and then walk farther ahead than your eye might have guessed, because the machine believed in the future location more than your nerves believed in the present shape. Between sight and barrel ran a chain of comparators and follow-up motors. The principle was simple but powerful. The gun mount kept asking whether the current pointing matched the commanded lead. If not, motors moved until the error shrank to zero. A human could never make those corrections as frequently or as finely without over-controlling in a panic. The sight was a hand that did not tremble, and the mount was an arm that did not get tired. This freed the gunner to do the part only a human could do well, keep the target tracked calmly in the glass and choose which threat deserved priority, while the analog brain did the part that machines do best, which is steady, repetitive adjustment under stress. None of this would have mattered if each turret had behaved like a proud island. The B-29's scheme refused that loneliness. It allowed more than one sight to call a turret, and more than one turret to answer a sight, under a logic called priority and assignment that was as much doctrine as wiring. A tail sight could demand the upper rear turret's attention if a fighter sat in its lane. A waist sight could borrow the lower turret if a belly pass developed. The pilot did not arbitrate with words in the heat of a pass. The system and gunners did by design. The effect was to pour the airplane's total firepower onto the most dangerous axis without delay, while leaving other quadrants covered by the remaining mounts. Concentration without chaos, that was the silent promise. A fighter pilot making a slashing attack expected to meet fear and delay. He expected his quarry to flinch and weave and wait too long to swing the guns. He counted on that. What he met instead, when this system was tuned and manned, was a serene mechanical patience. The sight stayed level. The reticle did not lurch. The guns moved like a clock's hands racing to midday. Bullets stitched toward where he would be, not where he had been, so that his clever curve turned treacherous, pulling him into a crossing pattern already filled with lead. And because the guns were stabilized and the mounts were servos rather than direct grip mass, the burst was not a spasm but a firm line. The fighter either broke away early or accepted a duel with a machine that never gasped for breath. This quiet computation demanded care before flight. Mechanics checked backlash in gears, and play in bearings. They spun up gyros to see if precession behaved within limits. They confirmed that a tiny twist at the sight produced a proportional, smooth motion at the barrel stops. They cleaned connectors because dust is a false prophet in any electrical system. It teaches the circuit to stutter and then to lie. They measured motor brushes and replaced them in daylight rather than at midnight on a line after a failure. The gunners met them halfway, learning how to track without jerks, how to accept the sight's steadying instead of fighting it, how to trust lead that felt excessive to a gut raised on iron sights. In that handshake between maintenance and method, the other computers came alive. There was a moral component to this mechanism too, though no one wrote it down on a placard. If the bomber could defend itself without violent, last-second thrashing, it could keep its promise to the bomb site up front. The fire control computers bought steadiness for the final run the way a good guard buys sleep for a town. And the bargain ran in the other direction. Because the nose would not wander in the last half-mile, the formation did not string itself out, and a lone, vulnerable duck did not lag where a hungry predator could peel him off. Precision and protection were not separate chapters. They were a braid, tightest where the enemy's teeth were sharpest. When stories later tried to separate the bomber into departments, the nose did this, the tail did that. They missed the point the machine made every time it climbed to its height. The airplane did not pass itself. It behaved as a choir that practiced until the notes came in the right order. The guns did not ask the nose for permission to be steady, and the sight did not ask the guns to be brave. They simply kept their ends of the same bargain. And the sum was a weapon that confused attackers because the weakness they had trained to exploit the human need to flinch and fumble at the last instant was hidden behind a layer of servos and gyros that did not share that need. To people who expected a duel of nerves, it felt unfair to meet a duel of mechanisms. But that is what modernity is in war. A steady hand hidden inside the human one. Strip the paint from every legend and lay the bare machine on a bench, and what remains is a certain seriousness about small truths. That is the first interesting fact about this design. It is not a celebration of one brilliant box, but a discipline of fits and tolerances, of unglamorous parts that behave well together. The sight's gyros are only as good as the gimbals that cradle them, which are only as good as the machinist's feel for play measured in thousandths, which is only as good as the inspector who refuses to sign his name over a bearing that sings the wrong song, which is only as good as the packing that keeps that bearing clean on a salt-air pier and the crate that keeps the bearing safe on a train. Precision begins far from the runway. It begins wherever a rule about dimension meets a human hand that cares. The second interesting fact is that the airplane was built to accept such seriousness, not as an exception, but as its native climate. A bomb sight that can drive an autopilot is useless in a cockpit that cannot accept tiny corrections without a fight. The flight controls, the servo tabs, the linkages, these must be free of slop but not so taut that they chatter. They must be responsive but not skittish. In the same way, a turret that can move with grace is an embarrassment in an airframe that shudders with every engine pulse. The design of the big pieces, the wings and fuselage matters because the little brain inside them depends on a world that is more pond than rapids. Engineers sometimes speak as if the clever part sits in the boxes. In truth, the clever part sits in the promise that the boxes will live in a platform calm enough for their small corrections to dominate. What also invites respect is redundancy without waste. The gyros do not live alone. They have backups, and faults are meant to fail safe instead of failing wild. Wires are routed away from hot places and sharp edges, because a cut in a cable is not a local sin. It echoes through the system in sudden nonsense commands. The autopilot can decouple from the sight at a switch, because pride is not part of the design language humans retain vetoes when the machine misbehaves. And when components drift, there are adjustment points within human reach. The machine is neither sealed in mysticism nor exposed as a tangle of uncontrolled tweaks. It is a garden with paths. You can prune where intended and leave the rest to grow. Training is a designed component. That is easy to say and hard to live. The syllabus for the men who used this equipment was not a stack of folklore and scoldings. It was testable steps, repeated until muscle memory grew. The navigator's method for measuring wind drift is not a ritual. It is a way to buy the bomb sight the only gift it truly needs: honest numbers. The bombardier's coupling procedure is not a superstition. It is the shortest path from on course to stay on course. The gunner's tracking drill, practiced until the sight picture remains ordinary, even when tracers write their bright grammar around the canopy, is not about bravery. It is about making the analog computation sing its song without the squeal of human panic. The machine keeps its end of the bargain when humans keep theirs, and the bargain is written down as a method, not whispered as a myth. Maintenance, too, is not a penalty, but a feature. The components are accessible because they must be checked. Panels open the way a good book opens, without cracking the spine. Test points are where instruments can reach. Calibration rigs exist on the ground that replicate the stresses aloft, so the first time a flaw shows itself is not at 20,000 feet. Consumables are named as consumables, with expected lives and replacement intervals that make failure the last surprise rather than the first. It is fashionable to admire devices that just work. It is wiser to admire devices that work because people can keep them working. The interesting thing about the B-29's brains is that they were not divas. They were professionals in overalls, and they demanded companions in overalls to match. Then there is the human-machine handshake, which the design treats with respect. Knobs are shaped for gloved fingers. Switch guards exist because the cost of a clumsy elbow is higher than the cost of a gram of aluminum bent into a little fence. Indicators are placed where a field of view matters, not where a draftsman found an empty square on a drawing. The airplane is not merely a carrier of devices. It is a theatre where human eyes and hands must perform under light that changes from dawn to dusk to moon, under cold that creeps and noise that nags, under fear that begs for shortcuts. The design meets that theatre halfway. It declines the romantic idea that people will be perfect. It builds for people who will be good enough if the stage helps them. Finally, the most interesting thing. The system is humble about authorship. When it works, credit is hard to assign because so many quiet agreements held. A bearing rolled the way it was supposed to roll. A wire carried a signal, and then did it again tomorrow. A gyro spun at the right speed because a mechanic listened for a wrong note and did not hear one. A bombardier set wind honestly and left his pride outside the glass. A gunner tracked with a soft grip and let the sight lead his arms. In a world that rewards singular heroics, this is boring. In a world that cares about results, this is the only kind of excitement worth having. The design is interesting not because it is clever in one place, but because it is modest in 100, and together those modesties behave like genius. When an airplane falls, the sky keeps few secrets. It scatters and sears, but it does not erase. Men with canvas bags and notebooks learned this truth the hard way, as they hiked to craters, searched paddies and riverbanks, and followed the pointing fingers of farmers who had watched something silver trail, smoke and stagger. They came with a way of seeing, trained to look for numbers stamped into small pieces of metal, to read the ghost of a machine out of what the fire had spared. They found pieces of a bomb sight hood lying like the shell of a small animal split open. They found gyros with their rotors fused to housings by heat. They found blackened looms of wire that told little stories about where current had run. And they found, sometimes intact enough to photograph and sketch, the turret sighting stations and the servo housings that had moved the guns. In workshops with bare bulbs, on benches that had seen bicycles and army trucks before they bore the weight of this new puzzle, the pieces went under calipers. Machining was the first surprise. Edges were chamfered with a kind of care that felt domestic rather than hurried. Gear teeth were finished with a polish that caught the light. Bearings felt free without slack. Screws seemed to belong to their holes like ring fingers to rings. The men from these teams were not fools or awed children. They were practical mechanics and engineers used to tight budgets and clever workarounds. They recognized the difference between decoration and tolerance. What they held was not decorated. It was true to its lines in a way that spoke of factory time spent on inspection and of a supply chain that had learned to keep quality from collapsing as quantity grew. They traced circuits from connector to connector, mapping how a whisper from a sight head would turn into a push at a motor. The logic was not obscure. It was, if anything, plain to the point of annoyance. Measure a rate. Compare it to a desired rate. Move until the difference goes to zero. But when the sight was set back in its cradle, and a gyroscope was spun by an external drive to simulate life, the system's serenity was disconcerting. It refused to twitch. When they hand-moved a pivot to stand in for an airplane's roll, the follow-up left no gap they could see. It was hard to find an explanation that honored both the simplicity of the logic and the sophistication of the behavior. Many fell back on the only honest words they had. It is well made. It is well integrated. The bomb site's insides offered a different kind of frustration. Here, cams cut to shapes that encoded ballistic curves gave up their meaning only if you already knew the story they told. You could copy a cam's shape easily enough with a tracer. You could even make a brother to it with a good mill and patience. But the cam, without its gyros, without the autopilot cables, without the exact friction that the designer had expected in his mechanism, was a mute cousin. The men understood this. They could reverse draw each part. They could not make the bench behave like the sky. So they did the next sensible thing. They tried to reassemble subsystems to see them talk to each other. It was then that the third frustration arrived: calibration. Every linkage wanted a setting. Every setting wanted a tool. Every tool wanted a procedure. You could not substitute confidence for any of these. Confidence is not a shim. Reports filled with phrases that were both precise and powerless. Excellent finish. Good fit. Clever feedback. High-quality insulating varnish. The words stacked up without giving a simple handle that a manager could pull to say, "Make me one, and make it work tomorrow." There were also the sour notes that any team will write when pride is involved. Complaints about overcomplication were so many parts truly necessary, and about the foolishness of placing faith in a site that would obviously be fragile in combat. Those notes had their own honesty. Any machine that depends on a faithful chain of small, delicate truths is a machine that offends the spirit of a fixer who loves the violent certainty of a hammer. Yet even those notes could not make the demonstration on the bench lie. Spin the rotor, and the picture stays level. Feed a signal, and a motor moves as softly as a cat's side rising in sleep. The bench would not agree to resentment. On rare days, when a component was almost whole, there was the temptation to declare it understood. A servo amplifier could be made to amplify. A rate gyro could be replaced by a local cousin. But the moment those pieces tried to work with one another, the small mismatches shouted themselves hoarse. A connector spec that seemed trivial became a source of noise. A bearing with a little more drag became an infant's clenched fist in a mechanism that expected a pianist's fingers. The men kept notes about these embarrassments because honesty on paper is cheaper than a lie in production. Over months, they built clever imitations that gave glimmers of the original behavior. A site could be persuaded to hold something like level, but it needed to be begged and bribed. A turret could be taught to lead, but it gulped current and shook. The copy wore its strain on the surface. And always, beyond the bench, there was the doctrine built into the original. The airplane assumed a way of flying. It assumed that crews would measure wind instead of guessing. It assumed that pilots would give the bombardier the final say over the last minute. It assumed that gunners would accept stabilized sights and allow their hands to be led. The men in the workshop could not copy that doctrine with a lathe. When they wrote their conclusions, they were finally frank about it. The precision was not a trick inside one box. It was a culture organized into metal. In quieter moments, they called it by a simpler name: a system. The hardest truths are not hidden. They are ordinary and connected. The first difficulty was integration, the way each device's small honesty depended on the next device's small honesty. A bomb site's elegance meant nothing if the autopilot could not accept its whispers without adding its own hum of error. A turret's quickness was useless if the sight that commanded it could not stay level under the kind of bumps that airframe and weather routinely supplied. Integration is not an afterthought. It is the condition into which parts are born. Copy a single component, and you have a trophy. Copy the relationships between components, and you are at last somewhere near the original. That second task is more art than shape tracing. It asks you to reproduce tolerances and response curves, not just look-alike silhouettes. Calibration was the second difficulty, and it is a cruel one because it looks like fussiness until the moment it reveals itself as necessity. Every linkage wants a starting point, every sensor a zero, every amplifier a gain, and a bias that put its behavior in a window where the rest of the system expects to meet it. The problem multiplies as the number of parts grows. You can set one thing right by hand. You cannot hand-tune 50,000 things across a fleet and keep them that way without tools and methods that bend the average toward truth. In the original system, those tools and methods existed as test rigs, plug-in gauges, and checklists that crews could run in their sleep. In a copy, without those, the same mechanism looks like a liar because it whispers the wrong number with great confidence. And when a wrong number is fed to a bomb site, the bombs land where the wrongness points, not where hope points. Manufacturing tolerance at scale made the third barrier, and it made it tall. A single bearing, polished by a master with time to spare, will give a moment of silk to a bench test. 10,000 bearings, bought under pressure, will tell a harsher story. Gears cut on a tired machine do not mesh like gears made on a fresh one. Wires drawn from copper that saw a little too much impurity crackle at the edges of loads that clean copper carries in silence. Varnishes that should be cousins act like strangers under heat. Paint that should insulate decides to conduct after a wet season. No drawing captures these human and material truths. Only a factory discipline, grown over years with inspectors who mean their signatures, can keep them from spilling into the final assembly as a fog of small sins. Precision is allergic to fog. Doctrine was the fourth barrier, and it is the one that wounded pride most because it is not in the parts at all. It is in the people. The original system relied on crews who treated numbers as serious and procedures as a kind of faith. They did not eyeball a wind because the sight did not reward eyeballing. They did not try to outfly a coupled autopilot in the last seconds because the sight's brain was better than their wrists at holding a line. Gunners did not snap their wrists to catch up with a crossing target because the lead would take care of itself if they simply tracked. This is not to say they became passengers. They became partners who knew when to act and when to let a machine act. Without that doctrine, the same hardware is asked to do a different job, and it fails not because it is weak, but because it has been asked to be something it never promised to be. There were smaller barriers hiding inside these large ones. Noise in circuits that were drawn beautifully, but assembled with wire that picked up whispers from adjacent runs. Friction introduced by a sealant chosen for supply reasons rather than performance. A switch with contact bounce that an amplifier magnified into a twitch visible at the barrel or the elevator. Each of these alone is a problem for a patient afternoon. Together, they are the texture of a lost cause. You can spend a week killing one ghost and discover that you have, with the same effort, made two cousins of the ghost stronger. Systems punish those who fight them part by part. The summary, written without malice, is that explanation failed because explanation wanted a villain or a hero. It wanted the precision to live in a single cam, a brilliant servo, an exotic gyro. It wanted to say, copy this shape, steal this device, learn this one trick. But the truth was that the precision lived in the way honest parts met honest procedures in an honest airframe. It lived in the repeatable acts of calibration performed at dawn by men who did not need to be told twice how important their checks were. It lived in the decision to let a bomb sight fly the last half mile because that is what it was made to do, and in the humility to feed that sight the right numbers. It lived in the refusal to allow slop into bearings and excuses into schools. To explain that to a commander who wants a lever to pull is to confess that there is no lever. There is only work, done the same way, every time. So the engineers who wrote their reports fell back on the polite words that technical people use when the shape of a problem cannot be bent into the shape of a quick solution. They said the machining was excellent. They said the integration was sophisticated. They said the tolerances were tight. They said the system rewarded training. These are all true, and none of them, alone, is the truth. The unglamorous fact is that the enemy's precision came from an ecosystem that took years to grow and could not be transplanted in a season. It was not a secret. It was a culture. And cultures are not explained. They are lived, or they are not. It begins with the promise of a long-range airplane that will carry its own calm with it. On the ground, crews practice coupling a sight to an autopilot until the motion feels like a handshake rather than a trick. Early missions teach hard lessons about winds that move like rivers in the sky. Even a perfect machine cannot correct for numbers it is never given. So the first phase is humility. Learn the air, measure the drift honestly, and prove that the little signals traveling from the nose to the control servos will keep their strength when the ship is heavy and the weather is restless. In this period, the results are uneven, but instructive. A steady run becomes a thing to aim for, not a luxury, and formations begin to value the quiet minute before release as the most expensive minute they can buy. The next phase is confidence earned by repetition. The site's procedures stop feeling ceremonial and begin to feel like the only sensible way to fly. Bombardiers settle into a rhythm. Measure, set, couple, watch. Pilots discover that the light touch the autopilot prefers is not an insult to their skill but a path to performance. Navigators refine wind estimates with enough conservatism to keep the math on the safe side of truth. On the gunnery stations, the stabilized world inside the site starts to feel more real than the buffeting world outside, because it is the one that yields predictable results. The airplane's brain is no longer a novelty that must prove itself. It is a partner whose reliability sets the tone for the crew's patience. Results begin to cluster. Maps that once showed ragged impact patterns now display ovals that tighten, imperfect but persuasive. Weather pushes the system into a third phase. Clouds mean that the glass nose sees only white. So the bombing solution must sometimes be referenced to a picture that comes from a radio wave rather than from the naked eye. This is no small change, but it does not tear up the compact the crew has with procedure. The essentials remain the same. Hold a level path. Feed a stabilized instrument. Honest inputs. Let the last seconds belong to the machine that was built for them. There are days when the result is more a proof of method than a perfect strike, and yet those days matter because they protect the habit of precision from being broken by impatience. The crew does not return to the old theatre of guessing. It keeps the new discipline even when the sky refuses to show its face. By the time the last phase arrives, the airplane's analog brain has migrated from being an object to being a culture. Young crewmen are taught by older hands, who have learned to spot the telltale signs of sloppy inputs, a drift measurement taken too quickly, a coupling switch thrown with a flourish rather than a check, a gunner who insists on forcing the mount rather than letting it lead. The admonitions are gentle because the proof is close at hand. A calm run and a clean release make their argument without needing a raised voice. The formation benefits in large ways that are not obvious to a single ship. Less stretching, fewer strays, steadier defenses, more bombs falling within a pattern that can be predicted and planned against. From the outside, this might look like a technical evolution. Inside the fuselage, it feels like manners, the kind that keep a crowded table from turning into noise. If the story were told only in dates and milestones, it would miss the human texture that mattered most. The airplane's brain did not arrive in a crate labeled precision. It arrived as a series of expectations that had to be met each morning. The timeline is simply the order in which those expectations became normal. First came the belief that small corrections could do large work, then the patience to let those corrections accumulate, then the proof that a steady crew could hold a straight line in crooked air. Finally, the recognition that an army of practical acts, calibration, training, maintenance, procedure, could be arranged into something that strangers would mistake for mystery. That is the end of the line and also the beginning, because once a method is normal, it becomes invisible. What remains visible is the map after the mission, with marks grouped where the plan said they should be. Stories breed in the space between what a machine does and what a person feels while it does it. One story says that the bomber's aim was an illusion, that men in the nose still relied on instinct, that the site existed to comfort headquarters rather than to guide iron. The reality is less dramatic and more dignified. Instinct can set a course and choose a turn, but the last half-mile is a narrow hallway in which instinct makes noise. The site and its gyros do not care about nerves. They are not impressed by a firm jaw. When the inputs are honest, they will walk the ship to a release that occurs because a set of rates and angles has reached a conclusion. The human part that remains is judgment about when to begin and when to trust. Everything else is the arithmetic of motion turned into control surface. Another story insists that a single captured device would unlock the secret, as if the precision were a spell written on a piece of paper. This belief confuses a tool with a trade. Any one box can be copied if given enough time and patience. But the box does not keep its promise by itself. It keeps its promise when mounted on a base that matches the designer's assumptions, when connected with wires that carry clean signals, when fed by hands that have been told the truth about drift and speed and height, and when listened to by a pilot who has consented to let it lead. The device is a noun in a sentence written in verbs. Without the verbs, it is a souvenir. There is the darker myth that gunners sprayed in hope and called it fire control. Hope is never absent in combat, but hope does not move a turret with that smoothness or hold a level sight when the airplane twitches. What moves the turret is a small comparison between where the guns point now and where they must point to put bullets where an attacker will be. And that comparison happens hundreds of times a minute until the error is gone. What holds the sight level is a rotor that refuses to be bullied by a bump. The man at the site brings the one thing the machine cannot bring: calm attention, and his calm is multiplied by mechanisms that never taught themselves to panic. The spray exists in memory because it is loud and dramatic. The line that stitches through a crossing path exists in results, which are quieter and harder to tell stories about. There is a final myth in which the entire scheme is portrayed as fragile, a vase among hammers. The reality is that the components were built with the kind of endurance that comes from being meant for the field. Panels open without a fuss. Bearings are sized for dust and time. Connectors are chosen for the number of hands that will grasp them, not for the boast on a drawing. When things break, they break like professionals, showing their wounds cleanly rather than poisoning the system with half failures. This is not romance. It is engineering that has met logistics. The brain was never a diva. It was a worker with a badge and an assigned shift, and the shift did not end until the airplane was tied down again at night. The truth that survives the myths is both less glamorous and more sturdy. The airplane achieved its precision not by escaping the world but by agreeing with it. With the wind's push, with the pilot's limits, with the gunner's capacity for steady tracking, with the machinist's reach for the thousandth of an inch. Agreement is not a headline, it is a habit. People who expected to find wizardry in a single shining part were disappointed. People who looked for a method found one, and they found it written into metal in a way that could not be denied by opinion. The myths persist because they are easy to retell. The reality persists because it leaves marks on maps and holes in metal, and those are eloquent enough. It is comforting to imagine a single mind at a drafting board, drawing a plan that bends an airplane to his will. The truth looks more like a procession of decisions, none grand on its own, each necessary to the next. The first decisions belong to factories that accept or refuse the quiet tyranny of tolerance. An inspector chooses not to sign for a bearing that feels wrong under a fingertip. A line chief decides that every 10th unit will be pulled for a deeper look, even when schedules are blunt instruments pounding on his door. A supplier swaps out a batch of wire after a test shows a hairline tendency to arc under heat. These choices do not know the names of cities on a target list. They are simply votes cast for small honesty. Yet their ballots are counted in the nose of a bomber when a sight settles without a shiver and a servo obeys without delay. The next decisions belong to teachers. A syllabus tightens until it becomes a sequence that can be learned by men who are tired and may be afraid. The staff who write these checklists have no medals for their work. They care about items in the order they must occur. They remove jokes from the margins. They add a line that reminds a bombardier to confirm his altitude against the pressure setting, not because someone once forgot, but because people do forget, and the system is designed to forgive only what it can afford to forgive. In a warm room with maps on the wall, an instructor repeats that the coupling switch is not a moment for flair, it is a moment for a breath and a glance. He repeats this enough times that the breath and the glance become normal. Maintenance chiefs and their crews decide the rest on cold nights under open hatches. They choose to rebush a joint because the play is not yet a crime but will become one. They choose to change a motor brush shy of the published limit because waiting would be false economy. They add a drop of oil where a drawing says the reserve is enough, because the drawing was right for a perfect world, and they work in the world that dust owns. They keep a set of bench rigs in a corner that let them spin a gyro and see if it sings the same note it sang last week. They are not paid for their affection for order, but they act as if they are. The airplane's brain rewards them by refusing to surprise their friends in the air with the kind of failure that begins as a shrug and ends as a crater. Finally, decisions are made in the cockpit and the compartments by men who have earned the right to be proud and choose not to spend that pride where it will do harm. A pilot hands the last minute to the bombardier and does not take it back out of boredom or doubt. A bombardier sets wind with care even when the briefing's numbers feel close enough. A gunner refrains from forcing a mount because the site's lead is going to carry the day if he tracks clean. The navigator tells the truth about drift even when truth is inconvenient to a schedule everyone wants to make. None of these men think of themselves as judges on a bench. They think of themselves as teammates. Yet in the simplest sense, they are the authority that matters most, because they either allow the system to be itself or press it to be what it is not. Ask who decided this precision, and the answer comes back as a list of people whose work is rarely in the frame of the famous photograph. The engineer who drew the cam profile, the machinist who refused to round off a corner that wanted to be sharp, the production controller who fought for the delivery of varnish that behaved under heat, the instructor who borrowed an extra hour so that students could practice coupling until boredom gave way to grace, the chief who set aside a day to purge a squadron's connectors of dust, the crew who chose to be gentle in the very moment when gentleness is hardest. They are the court that granted authority to the numbers. They did not sign an order to make bombs fall true. They made them fall true by doing the next careful thing and then the next. The airplane's analog brain belonged to a war and a season, but the idea it proved does not age. The idea is that precision is a conversation between design, manufacture, procedure, and character. Design draws the lines that allow small signals to move big things. Manufacture decides whether those lines will curl under pressure or stand up. Procedure ensures that the signals are fed into the right doors in the right order. Character makes people tell the truth to their instruments and trust the answers when the answers arrive. Remove any one of these, and the word precision becomes an advertisement instead of a promise. Keep all four, and you can do remarkable work with parts that are, in themselves, entirely ordinary. What endures from the sight and the servos is the respect for stabilized truth. In any era, the world shakes, data is noisy, hands are human. A device that stabilizes a view, whether it is a glass reticle or a modern sensor, is not a luxury. It is the ground on which judgment can stand. The bomb site's gyros declared a small independence from turbulence so that the rest of the system could behave as if it lived in a calm universe. That is a lesson worth carrying anywhere that decisions must be made while the floor moves. Make a piece of calm, or borrow it from a tool that can, and let your best thinking live there. What also endures is the refusal to worship single parts. The temptation to label one component as the secret will always be strong, because secrets are satisfying and parts can be held in the hand. The B-29’s brain teaches the opposite. The most powerful thing in a complex system is not an individual object, but the agreements between objects. The agreements here were measured in thousandths and in steps on a checklist, in torque values and in the habit of waiting 1 extra second to let a gyro come fully to speed. Agreements like that still pay dividends, whether the signals are analog voltages, digital packets, or the pressure of a hand on a control column. It is the fit that performs, not the shine. Another durable lesson is the humility to let machines do what they do better than people, and the insistence that people do what machines cannot. The site flew the final run with a steadiness no human could match, but a human chose the line, read the weather, and accepted or rejected the picture. The turret system led targets with a patience that nerves rarely sustain, but a human decided when the threat was urgent and when ammunition should be conserved. Today the nouns change, yet the division of labour remains. Give calculation to the thing that calculates without fatigue. Keep judgment in the hands that can be taught wisdom. The partnership is where the power lives. Finally, there is a moral thread that survives the hardware. Precision, honestly sought, is a form of restraint. It tries to make force answer to aim. It resists the lazy spread of effect into places it does not belong. That restraint is not softness, it is rigor. The crews who measured drift, rather than guessing, did not do it to please a manual. They did it because they owed their effort to the cost of the mission and to the people who would live or die by where the bombs fell. When Japanese engineers later handled the parts and admitted that the behavior in the air was hard to explain on the bench, they were recognizing that a culture of restraint had been built into metal. The culture said, "Be exact where you can, be steady when it counts, and earn your results by method rather than luck." The airplane that carried this brain has long since become a museum piece and a story. The gyros have spun down, the servos sleep, but the shape of the achievement remains useful to anyone who must make consistent decisions in inconsistent conditions. Stabilize the view. Tell the instrument the truth. Let small corrections work over time. Maintain the links that make separate devices a system. Teach the method until it becomes ordinary. These are not glamorous instructions. They do not make for easy legends. They simply work. And in that refusal to rely on the dramatic, the old machine still speaks to the present with a voice that is quiet, precise, and hard to argue with.